Hello everybody, this is Scott Amos. Recently I've been working on the statistical aspects of my theory. This is my new website, and it lets you calculate the statistical significance of the observed hierarchy, and you can switch various measurements on and off, and the odds change accordingly. So with the default selection, it's 1 in 162 million. So that's pretty good. It's beyond sigma 5. And then a few days ago, I also calculated odds based on agreement and value. But here in this method, I basically set a fixed range, 6.666 until 6.676, and then looked at how many possible values agree as well as the observed value or better. And so that's how you get these scores here. And because there are 11 different possible values between here and here, so that's why the denominator has 11 here. And depending on the digits, it will be more like 101 and so on. The good thing about this method is that it won't give you very exaggerated p-values for a single measurement, but it's not necessarily the most logically sound method, because the null hypothesis is obviously that that general relativity is correct, but then you would expect the g-value to be the Kodada recommended value, which is 6.6743, and not a free range here. So having a free range is okay if you calculate the odds based on a hierarchy, because then the null hypothesis basically that there's no pattern at all, and so it's just pure randomness. But when you calculate p-values based on agreement and value, you can't possibly use pure randomness as the null hypothesis. You have to have one value that is the null hypothesis. And so when we do that, we get a different answer. And so for these different measurements here, we get various odds. Here, 0.46, close to random chance. So these here are calculated by using the standard deviations. We have the measured value, the standard deviations, the predicted value, and that has certain standard deviations, 0.000228. And so all these are pretty normal p-values for single measurements. But then we have here two extreme cases, one based on Parks, one based on Schlaminger, from this year, his Sapphire measurement. So the improvement here, so using my theory, this result is 1.16 times more likely. So, and then we can transform that into a p-value. But for these two cases, it's quite an extreme value. Here we have 1.7 to the times 10 to the power of -6, and here to the power of -18. So that's what's those two are the main drivers of this very extreme p-value here. It's 1.19 times 10 to the power of -17. But if you want to exclude those two extreme measurements, let's say we exclude them, then we get something more conservative, 0.017 or 18. So yeah, this method is highly sensitive to extreme cases. So maybe for this method, it's best to just refer to just to look at the p-values of individual experiments. But it's both to have it's good to have both types of p-values. Well, now we have 3 different types of p-values. The one based on the fixed range, which you could say it's still a very legit p-value. It's just that it's a p-value that you would have if there was no gravity theory at all before, and then suddenly you have SPD quantum gravity, and that's the p-value you would come up with, because you wouldn't assume any value for big G, and your theory predicts this value or that value. And it's really a big strength that it's not sensitive to extreme outliers in the sense of p-values. So yeah, so that's what I've been up to, and soon I will get those new types of p-values up on the website as well. I have a very good programmer, she can do that. Okay, that's all for now. See you.